Section 6.2 is on line fitting, residuals, and correlation. The first learning objective is to discuss the difference between correlation and causation. Correlation means that two variables are related, that there is an association between them. We measure that using the linear correlation coefficient, which has the symbol R. If R is close to 1 or -1, it indicates a strong linear correlation between the two variables. If R is close to 0, it indicates a very weak relationship between the two variables. Causation means that one variable causes changes in the other variable. As we discussed in Chapter 5, we can only determine a cause and effect relationship between two variables if it's a valid experiment. In order to have a valid experiment, we need to satisfy the principles of experimental design, which are controlling, making it so that the observational units in each group are as similar as possible. Randomization, randomly assigning individuals to at least two different groups, and then replication, having at least two individuals in each of those groups. So let's look at this example. For a random sample of 100 American cities, the linear correlation coefficient between the number of robberies last year and the number of schools in the city was found to be R equals 0.725. What does this imply? Does this suggest that building more schools in a city could lead to more robberies? Why or why not? What is a likely lurking variable? The correlation coefficient R is 0.725, which is pretty close to 1. That indicates a pretty strong positive linear relationship, meaning that the number of robberies last year and the number of schools in the city is related. However, is it a cause and effect relationship? Well, this is not a valid experiment, and so we can't say that building more schools in a city would lead to more robberies. We would not say that building more schools causes more robberies. The reason is because there are other variables that actually could cause both a need for more schools and a higher number of robberies. So there is a fairly strong correlation between the number of robberies and number of schools in the city, but this does not imply that building more schools will lead to more robberies. A likely lurking variable is population. When the population is higher, more schools are built, but there's also more crime. Next example. A random sample of 200 men aged between 20 and 60 was selected from a certain city. The linear correlation coefficient between income and blood pressure was found to be R equals 0.807. What does this imply? Does this suggest that if a man gets a salary raise, his blood pressure is likely to rise? Why or why not? What are likely lurking variables? Again, this is not a valid experiment, and so therefore, even though our correlation coefficient of 0.807 indicates a positive relationship between income and blood pressure, it's not a cause and effect relationship. There is a positive correlation between income and blood pressure for men aged 20 to 60, but it does not mean that if a man gets a salary raise, his blood pressure is likely to rise. Higher stress jobs likely earn more money, but higher stress also likely increases blood pressure. So stress level is one lurking variable, a variable that's not the explanatory or the response variable, but could be affecting both of those. Being in a supervisory position increases salary, but also increases responsibility, which could also raise a man's blood pressure. So responsibility or position at work are other likely lurking variables that could be affecting both income